Hi everyone, I hope you're well. This year, our cohort of students at Atlas had a bunch of awesome, great questions that were extension to what we learn in Module 7 and also what we talk about during our HSC prep courses. So this video is meant to cover that sort of extension content. These are the sort of questions about double and single slits that you may have yourself. For example, how the patterns that we see are impacted not just by the slit separation, but actually by the size of the slits themselves. You might have questions about how diffraction actually works in the first place and what does it mean to have more diffraction in a context like a double slit experiment. Oftentimes we use this, we say, oh, more diffraction happens as sort of a throwaway line without really going into what it means. And I also had some really great questions from students that were really trying to hone in on how does the size of the slit need to compare to the wavelength of light in order for you to actually see a diffraction pattern. Because there's actually quite a few answers out there when you first look into this. This video is meant to try explore as much of this as possible in a comprehensive, rigorous, and fast way. And noting that the only thing that's explicitly in the New South Wales high school syllabus is double slits and the impact of slit separation or lowercase d. Single slits and slit width aren't explicitly talked about in the syllabus, but understanding them might help you out a bit anyway. Let's go. First thing is, recall what we're talking about here is single and double slit experiments. So when we incident light on thin single or double slits, what we see is a diffraction and interference pattern, something that looks a bit funky like this. This is from Module 7, Topic 2, the wave model of light. This experiment is our best evidence that supports the wave model of light. We also want to recall that if this is a double slit, then this distance between the two slits is the slit separation, or the distance between the slits. We give it the symbol lowercase d in our HSC syllabus. And I also want to introduce something called the slit width, which is just what it looks like right there. We give it the symbol lowercase a in convention in physics. This is not explicitly talked about in the syllabus. The goal of this whole section is to get us to realize that the diffraction pattern of a double slit is related to the pattern of a single slit. And it's really actually just a superposition of a single slit pattern with the double slit pattern. Technically, it's something called a convolution. Doesn't actually matter which of these terms we use here. It's just adding the two or multiplying the two different separate graphs together, basically. Recall, a double slit causes further fringes to sit within the single slit envelope. If this is my single slit diffraction pattern, and then I add another second slit of the exact same size as that first one, then it's going to create a new pattern that looks like this. And what we critically see with this new pattern is that it looks like it sits within that first initial pattern. And so we call this first initial pattern the single slit envelope, because it's sort of like enveloping the entirety of our double slit pattern. Okay, so here comes the actual facts of what happens when you do experiments with this, and also when you run simulations with this as well, which is what I've done here to get all of these images from. If we look at firstly a single slit obviously doesn't have slit separation because there's no two slits that are separated. It's just one single slit. So all that matters is the slit width, which is our lowercase a. Increasing the slit width will decrease the spacing between the fringes in your pattern. So if this is a single slit pattern with a small slit width, if I now increase that lowercase a, that slit width, I'm now going to get a smaller fringe spacing. And so these fringes are going to be closer together, or in other words, I get more fringes as well. Okay. In a double slit, this is the one that's actually inside of the New South Wales syllabus, increasing little d will decrease the fringe spacing. So this is a normal double slit with a small distance between the slits. If I increase the distance between the slits, my pattern will end up looking a bit more like this. And what we clearly see is that, okay, this fringe right here is quite narrow. Sorry, it's quite wide. And then these fringes here, each of these fringes is narrower than that initial one. So all of the fringes are more narrow. So the fringes are spaced closer together. So there's more overall fringes. All of those are saying the same thing. I didn't plan for this, but I'll just do it now. In our syllabus, we have the equation d sine theta equals m lambda. that explains this perfectly, right? It's us increasing d, and as a result, for the same wavelength of light and for the same particular order, m, so the order fringe number that we're looking at, I'm going to now have a smaller sine theta, which means I'm going to have a smaller theta, which means I'm going to have a smaller angle, which means the fringes are going to be closer together. Notice the single slit envelope has not changed because we have not changed the slit width. What is the single slit envelope again? Well, it's each of these fringes that come in little groups, right? Each of those groups was one of our original single slits fringes, right? And we see that that group is the same size as that group's the same size as that. The single slit envelope has not changed from before. And then thirdly, and this is the one that's a bit weird, in a double slit, if we increase the slit width, we will actually decrease the envelope spacing, right? So here is a double slit with a certain slit width and a certain distance between the slits. If I now make each of the slits wider, then my new pattern's going to look like that. And so what I critically see is that my envelope, so this envelope, is now smaller, right? The single slit envelope that I originally got has now been narrowed in, and there's more fringes in that single slit envelope that I can see in my double slit one as well. Critically though, the fringe spacing of each individual fringe this time has not changed, right? So for every single one of these fringes, they are still the same as they were before, right? So contrast this change with the change that we saw on the previous slide. In this previous slide, the envelope has not changed, but the fringe, each individual fringe has. Whereas here, each individual fringe has not changed, but the envelope has changed. Now, what do we do in HSC? In HSC, we only care about the fringes. We only talk about the fringes, each individual one. We don't actually talk about the envelope overall because we only have that d sine theta equals m lambda equation, which means this is the only thing we ever talk about, right? But this is also a different factor that can also happen as well when we take into consideration slit width. Okay, so that's all three of these graphically representing your results. Hopefully you can digest it. What I want to do next is actually want to show you the exact same stuff again, but in graphical form rather than with images, just to hammer the point home again. Yeah. So I'm going to go back to my single slit. Increasing the slit width decreases the fringe spacing. That's my original single slit. I now make it a wider slit, and now it looks more like that instead. So what we notice is that the fringes are now closer together, so we have more fringes. I will say that the intensity that we're graphing out on this graph is not actually accurate. The only thing accurate about this is the fringe spacing. There's so many factors that we can take into account here that we're just not going to do to try to keep it simple. That's a single slit. Double slit, the thing that we're used to. Increasing your distance between the slits would decrease the spacing between your fringes, right? Increase the distance. So now my two slits are further apart, and now my fringes are closer together. There's more fringes as well. Critically, again, the single slit envelope has not changed. What does that mean? That means this shape here, which is the envelope that I drew, that we saw on the earlier slide, that envelope is still exactly the same as it was before. So it's just each individual fringe that has gotten closer and smaller. Finally, double slit, increasing the size of each slit without changing the distance between the two slits. This will decrease the envelope spacing. So what looks like this before will now look like this. So before, this was my envelope. I've only drawn the central fringe in, but it doesn't actually matter, right? And this is my new envelope, where the fringes of the envelope, probably shouldn't use the word fringe, but where the envelope is now narrower and spaced closer together, but each of those individual fringes is still lining up at the same spot as it was before. Yeah, exact same as before. So hopefully that makes sense in that context. That brings us to the second part of this video, which is basically answering the question, what do we actually need the wavelength of light to be in comparison to the slit width in order to see a diffraction pattern? Now, to answer that, we actually have to go into a bit more of the basics of diffraction first before we jump into that. So recall, what is diffraction? Diffraction is the bending and spreading of waves around obstacles and through gaps and things. That is true for all waves. So light waves, sound waves, water waves, all of them do it. In this context, of course, we're going to ultimately apply it to light waves. And critically, the amount of diffraction that occurs depends on the relative size of the obstacle and gap with the wavelength. The longer the wavelength we have, or the smaller the gap we have, the more diffraction that we see. What does that sort of mean? Well, look at these four examples that I have here from left to right. The wavelengths are all the same. Here, I'm increasing my slit size as I go from left to right. On the left, I have the slit size very small compared to the wavelength. And what we see is I have planar waves coming in, and then once they go through that gap, they come out and they fully bend all the way around once they exit. In the case where the wavelength is roughly equal to the slit size, I see a similar deal again, although we'll see on the next slide how they're slightly, in a couple of slides, how they're slightly different. And then if my wavelength is a bit smaller than my slit size, or my slit size is a bit bigger, I actually still get some bending, but it doesn't bend all the way around. Instead, I get these little things here, which are called the shadow regions or shadow zones, right? These are the regions where the wave doesn't actually bend all the way around. And in fact, if I have an even larger gap, slit gap, then I'll end up getting even larger shadow regions. Now, these are simplified diagrams. Of course, in reality, the waves actually bend a bit around on the edge there as well, and there's other factors, but we don't need to worry about that too much. If you don't believe me that this is a real thing that happens, here are some photos of water waves diffracting through different slits. Big slit on the left, small slit on the right. We notice on the left, there's these shadow zones and there's less bending. On the right, there's perfect bending. We get perfectly circular waves from effectively a point source of the slit once they leave the slit. Now, the key thing with this is this way of talking about diffraction is really helpful when we're talking about it in the macroscopic sense. So for example, if you have a room, you're in the room, and there's a doorway to the room, and then your friend's standing outside, maybe like 5 meters out. There's no direct line of sight between you and your friend or anything like that. If your friend says something out loud, you're still going to be able to hear them, even though there's no direct path for that sound to follow to reach you. And that's because the sound is actually bending around the obstacles and actually bending as it leaves the doorway into your room and everything like that. So it's filling up all of the space. It's bending like it is in these cases. So it's diffracting. Now, in these sort of cases that are macroscopic, so the big world that we actually experience, it makes sense to say that, more diffraction has occurred, more bending has occurred for longer wavelengths or for smaller obstacle sizes. Thing is, it's not really appropriate to use this when we're talking about diffraction patterns, especially for single and double slits. Here's why. It turns out, for a single slit, we can only see a diffraction pattern when your wavelength is smaller than your slit size, which is actually this scenario here, and then in some ways that scenario as well. Critically, these ones where we think of it typically as having lots of diffraction, these ones can't actually have any diffraction patterns going on. So if my wavelength is bigger than my slit size, I'm actually going to get something like this graphed out in terms of the angle after I leave, the angle of how I leave the slit, and the intensity of the wave that I see after it leaves. In the case where the wavelength is perfectly equal to the slit size, I get this perfect intensity curve that goes to 0 at 90 degrees. So notice when the wavelength is longer, it doesn't go to 0 at 90 degrees. So in that sense, for the longer wavelengths, it's bent around more. So the intensity reaches more on the sides, right? But to actually see a diffraction pattern, I need this third case where the wavelength is smaller than the slit size. There, do I actually see a diffraction pattern? If you want to look back here, you can sort of think of it as that's the only case where I can actually get the wave diffracting and interfering with itself is probably the word I'm looking for. Whereas in those previous cases, the wave's not actually interfering with itself, so I can't get these bright and dark fringes that I see here. Also interesting thing to note is you can sort of extrapolate this pattern out, right? From the bottom, I see 5 fringes. In that middle case, I see 1 perfect fringe. And in that top case, what I see is just the middle third of that 1 middle fringe, right? It's always sort of the pattern expanding to take up more space as my wavelength gets bigger or my obstacle and slit size gets smaller. Hold that thought. Okay, that's for a single slit. What about in a double slit? Well, it turns out in a double slit, you can still get a diffraction pattern regardless of the relative size of the wavelength and the slit size. Now, of course, this isn't true For all wavelengths, you still need to fit all of the other conditions, but this condition here no longer holds true for a double slit to get a diffraction pattern. And I can prove this to you by showing you that this is the double slit pattern you'd get if your slits were infinitely small. Your slits are infinitely small, then that is the pattern that you'll see. And you'll notice that the intensity doesn't change as I move along it. It's just the same intensity throughout. And I also get all of my nice individual fringes, bright and dark bands, clearly showing me an interference pattern. Another way to look at it is like that as well. And if we take this back to our understanding of the single slit interference pattern from here, what we're basically seeing down here is that it's still following the envelope. It's just that the envelope is, well, infinitely spread out wide. Right? It's if we take this pattern and we keep on going upwards and we keep on having a smaller slit size, then our fringe is just going to get spread out more and more and more until it's effectively just 100% at every single point. And we know that our double slit pattern just sits within that envelope of the single slit pattern, right? And that's exactly what we see down here as well. I hope this was helpful. Hopefully I made some sense. If you have any questions, feel free to reach out. Some further notes about all of this stuff, just so that we've completely closed the loop here. Is that we've only looked at the horizontal component of each of these slits. So we only looked at that x-axis. We haven't actually looked at what these patterns look like in the y-axis. To look at that and consider that, we can actually apply the exact same logic that we have for slit width and stuff like that, and just apply it instead of across this way, apply it across this way. And we'll actually see what we see in our 2D interference patterns in the real world. Another thing to say about all of this is those of you who are interested in learning further advanced maths and seeing how it applies, double slit and single slit interference patterns are actually an awesome application of something called the Fourier transform, which is a maths concept also taught early on in uni as well. Typically, when we think about the Fourier transform, what we're thinking about is a way that converts a wave. So let's say you have a wave that consists of many different frequencies, but all you're looking at is just that wave over time. A Fourier transform can take that wave and then give you all of the frequencies that that wave is actually consistent of. And somehow, if you actually think about it, it will make sense, but somehow that same concept is exactly the exact same concept as a double slit or a single slit and the diffraction pattern that we see. So in the fancy words, the diffraction pattern is the Fourier transform of the slits itself, which is ridiculous. And if you want to learn more about this, feel free to watch this video from 3 Blue 1 Brown about the Fourier transform. Thanks for watching. See you later.